Okay, so I'll be presenting this paper that I released last year, published at NeurIPS 2024, called Understanding Transformers via N-gram Statistics. So here's the agenda for today's talk. I will present the problem formulation, give an overview of the main results, and then do a deep dive into the main results. So the question that my paper wants to, was there a hand raised?
We can take questions at the end.
Okay. Okay. So the question that my paper attempts to answer is, how does a transformer-based large language model make use of its context when predicting the next token? Of course, this is sort of, well, one of the holy grails of trying to understand neural networks and large language models in particular. Let me first address sort of maybe a philosophical issue, but it's quite relevant, which is, what does it mean to provide an explanation? Because we're trying to understand a certain phenomenon. What do we mean by an explanation? And an explanation, well, there's the dictionary definition, but basically an explanation answers the why or the how, and it provides a mechanistic process. So you might ask, why is it raining? And the answer you might give is because there's some kind of precipitation in the atmosphere. So that's an example of an explanation. Let's contrast this with a description. And that's the definition of the description of it. What a description is in the dictionary. It's a spoken or written account of a person, object, or event. And it answers the what. And in contrast to an explanation, it doesn't require knowledge of the underlying process. So you might ask, what's the weather like? And you'll say, it's raining. That's a description. In contrast to an explanation, which might be in terms of physics and things like that. And so to go back to the original question that I'm attempting to answer, the approach that I take is to describe transformer predictions, not to explain them, because explanation is very hard, right? We have to go through and understand all the neurons and things like that. I'm going to describe them in terms of training data statistics. And so let's look at what that means under the hood. So I'm going to use n-gram rules as my mode of description. So let's take a look at this cartoon example. So suppose my context is the tired dog. And you can form various statistical predictors out of this context. So here I have three rules here, rule 1, rule 2, rule 3, and there are many others. And these rules are simple n-gram rules where you take, say, some subset of the context, you go through the training data and you count the various frequencies of words, and then you make a prediction based on those relative frequencies. So this distribution, P condition on dog, is the distribution on next tokens based on their relative frequencies in the context of dog. And likewise, the dog or the tired dog, etc. Right? And then you can ask, how often is it the case that when I take the rule that best describes what the transformer is doing, so the transformer for every context here, the tired dog, makes a prediction, you go through your list of rules and you find the one that best matches it with respect to some metric on probability distributions. And then you can ask, well, once I choose that rule, let's say it's rule 2, the rule given by the dog, how often do they make the actual top one, the same top one prediction? And the first result of my paper is that this number is quite high, maybe higher than you might have expected. So on this toy data set, TinyStories, 79% of the time, when you choose this best rule, you actually get the same prediction as the LLM. So this is a quantitative sense in which it's obeying an n-gram-like prediction. You could also think of it as a measuring of stochastic periodicity, since stochastic periods is sort of this common way that some naysayers say of LLMs think about language models. But this is basically a quantification of how LLM predictions can be described in terms of n-gram rules. So this is the first result. And again, this is just an overview of the results. I'll go into more details of what these this result is actually saying. But at a high level, it's saying 79% of the time you can find a matching n-gram description. Again, there's 4 of these results, and I'm just going to go over them very quickly, just so we get an idea of where where my work is going, and then I'll go into the details. The second main result is that you can look at the predictions that an LM makes and look at their variance. And by variance, I mean under different models with respect to different runs. And in this case, different runs, I just reshuffled the data set. I could have also changed the seed, but it was just simple enough to change the data set. And you have, say, n models, and they make different predictions given the context. And it turns out that if they end up clustering, in other words, they have low variance, they tend to be well described by some n-gram rule. Okay, so that's maybe a little bit surprising. So it's sort of basically saying that, okay, well, clearly you need to have low variance if you're going to be described by some fixed rule, but that's necessary, but it ends up being somewhat sufficient. So if you do different runs and they all tend to have the same predictions, you could tend to find an n-gram rule which sort of agrees with these predictions. So that's the second result. The third result is a curriculum learning type result, which is basically saying that as you train these LLMs and you look at what kind of rules they're most similar to, again, you have these families of n-gram rules, and you have some metric on the space of probability distributions. You find that they start agreeing with simple n-gram rules, basically rules that have a smaller context and therefore simpler, and then they start the predictions that they make start becoming more complex, as you might expect. And this result is a way of quantifying that. It goes from more simple rules to more complex rules. And finally, one cool result of my work is that I discovered a way of detecting overfitting without using a holdout set. So here's a train loss and validation loss from one of these runs where I deliberately tried to overfit by training on many epochs on a very overparameterized model. The train loss continues to go down, the validation loss goes up. And as I will describe later, these are various train and validation curves for a modified loss function formed out of n-gram statistics. And you'll see that here, both the train and validation curve increase and track this validation curve. So in other words, you can form some training statistics without using a validation set that sort of tracks, that is correlated with this validation loss going up. So this is quite a remarkable result, because typically, you can't really detect overfitting without using some holdout set, and here you can, is what I'm saying, using just training data. So I'll go over this in more detail once we get to the deeper dive. But this is just an overview of the kind of results I got from probing LLMs using n-gram statistics. Okay, so now let me start from the beginning with that sort of trailer and describe the setup and go through sort of this description in terms of n-grams more carefully. So the setup is the following. The main data set that I look at is TinyStories. It's this synthetically generated children's stories using GPT-4. And so you prompted, give me some children's stories about X, Y, Z with some constraints, and then you do this a bunch of times, and you get some diverse but nevertheless simple text that's in natural language, but is quite simple and therefore useful as a playground. It's a 480 million token data set. And the other data set I use just to make sure that the results extend to more complicated data sets is Wikipedia from Maths Text, and that has 4.4 billion tokens. The architecture I use is one inspired from Chinchilla, and it's trained using basically standard settings by now: cosine learning rate schedule, Atom, W optimizer. Just some more statistics. I mainly use 150 million model, but I train other sizes too, just to show that results are robust. I'm trained for 4 epochs, just so that you can see various n-gram statistics more than once if they're unique. And in the eval loss you can achieve on this data set is 1.11 nats. Very low because the data set is quite simple. And similarly for Wikipedia, I use a slightly bigger model, 1 billion, trained for 1 epoch, just to vary things up. And there the train loss is higher because it's a more complicated data set. It's 2.1 nats at the end of training. Okay, so this is sort of the setup in terms of data and architecture. Okay, so let's look at what an n-gram model is in review. So the simplest way you can model language is just based on co-occurrence of words or tokens, since we tokenize text. And the most basic n-gram model you can think of is one in which you give me a context. I take the most recent n-1 tokens. So here's my context C. I can enumerate the individual tokens in reverse order in terms of most recent, right? So C minus 1 is the most recent token, and then C minus 2 is the second most recent token, et cetera, et cetera. And what an n-gram model does in this case is it predicts the next token T conditioned on the n minus 1 previous tokens based on the relative count of T in the context. So star is just a wildcard character. It's any context that has these n minus 1 tokens as a prefix, and then this T in the numerator is just the weighted count of T. So the n-gram model is basically the most simplest model you can think of. It's just relative counts based on context. Okay? And this model goes all the way back to Shannon in his classic information theory paper. And he considered 2-gram and 3-gram models. But of course, you can consider n-gram models for higher order n. Now, I'm going to consider slightly more sophisticated rules. Those are the most basic ones. And you can think of these rules as being somewhat modeled off attention, which is a soft context selection. And of course, I'm thinking of attention because transformers are implementing attention. We have, for example, for each token in the context, so I'm going to form a set of n-gram rules. So I just described the simplest one where you fix an n and then you look at the most recent n minus 1 tokens and you keep them all. But you can do other things with the tokens and form other rules. So for each token, you can imagine what an attention mechanism is doing. It can keep the token, it can ignore the token or drop the token, or it can, what I call, marginalize the token, which is a kind of semantic averaging. That's a little bit abstract, but the point is, based on this sort of calculus, you can form n-gram rules based on what decision you're going to make on each token from the context. So let's look at an example. So suppose my context consists of blah, 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 the very tired dog. These are the 4 most recent tokens. And for each of these tokens, I have 3 choices: keep, plus, drop, which is a minus, or marginalize, which is a star. And just as an illustration, with these 4 symbols as my choice, so I keep the, I drop very, I'm going to marginalize over tired, and I'm going to keep dog. And what is the n-gram rule that I'm going to get from this set of symbols? It's the one that's going to predict the next token, T, based on the relative counts, where the count says I'm going to look at all 3 token contexts that start with dog, start with the, end with dog, and the second token is a wildcard. Okay? So you can think of it this way, right? Your job as a language model is to predict what the next token is, the very tired dog, right? The very tired dog, I don't know, slept, barked, ran, whatever, right? And what this is saying is that the corresponding rule here, which would denote R sub these sequence of tokens, what this rule says is I'm going to go through the training data. I'm going to look at all 3 token contexts that start with the end with dog, and I don't care what the middle token is. And then basically I'm going to do a weighted count of all these contexts, and then T will have a probability based on its relative frequency, right? So what this is saying is that I'm going to use these 4. I see all these tokens, and I'm just going to kind of look at the semantics based on the and some arbitrary token here and dog. Okay, so that's a valid rule, right? I could have taken all 4 tokens, but now I do this other kind of weighted averaging of all contexts. So that's an example of a sort of a way you can have a predictor based on a certain training data statistic obtained by this rule. Let's just do another example. This won't be a very good rule, but it's just to illustrate the point. Suppose I have these set of symbols, plus, plus, minus, minus. So here I have the very tired dog, and I'm going to do something maybe a little bit silly, which is just to ignore tired dog and keep the very. And in this case, the rule is I'm going to predict the next token based on all contexts that end with the very, which is going to be a pretty bad rule because the very tired dog, there should probably be a verb here, but that's very unlikely to be a verb here, right? But you're, but that's a perfectly well formulated rule. It just won't be a very good one. And you can do all kinds of variations of this. So anyways, the point is this: I'm going to formulate all these rules based on how many tokens I consider and what I do with each token. Do I keep it? Do I drop it? Or do I average over it? Do I marginalize over it? And the point is this: I now have a relatively rich set of rules. I can have rules that are based on the suffix, which are these classical n-gram rules, which basically I keep all the tokens where I keep up to m. Sorry, sigma is basically this tuple of plus, minus, or star, and this just means I keep up to m of the tokens. So m is basically the effective context length, and I can sort of keep only the suffix, and those are my sets of rules. These are the sort of classical n-gram rules. I can keep subset of tokens. So here I'm allowed to only drop or keep tokens, and again up to context size m. Or I consider the family R all, where I now allow arbitrary signature here, plus, minus, or star. So these are just different families of n-gram rules that are increasing in expressivity as I go downwards here and as I increase m. And so let me just reiterate. So there are those classical n-gram rules, and I'm just basically extending those rules kind of based on some intuitions about attention, where I can drop tokens or sort of do some kind of averaging. And the point is, once I have these families of rules, every time my candidate language model, a transformer, makes a prediction, I can ask, do any of these rules describe what the transformer is doing, right? Again, a description, not an explanation. I don't know why it might choose these rules, but do any of these rules give a good description? So going back to what I mean by description, for one of these rules to be a good description of what the transformer is doing, I have to basically quantify what I mean by the closest of two probability distributions, right? One probability distribution is a good description of another if they're close in some metric, right? So what is the metric I'm using to describe probability distributions? So I'm going to use a standard one, which is the variational distance. It's basically the L1 norm on vectors. In this case, it's just the sum of the absolute values of the magnitudes and just a factor of a half to normalize this distance. So this distance is bounded between 0 and 1 for probability vectors. And this is a sensible distance because it's symmetric and bounded, unlike the KL divergence, which is not symmetric and unbounded. And for concreteness, I'll also use top one accuracy between two probability distributions. In general, it's this fancy thing called the Jaccard index, but basically the top one accuracy is just basically saying, do P and Q, when you make the same top one prediction, do they agree or not? And this Jaccard index is just a way of doing tiebreakers, because P might assign equal mass probability to several tokens, and so it might, the argmax might have two values, and if the argmax of Q has one value, then this thing would be a half, because the IOU of a one element set with a two element set, and where that element is in the set is 1/2. So in general, this is just whether the top one predictions of P and Q agree, and if they're not unique, you just do this IOU thing. So anyways, so those are the two metrics I'm going to consider, basically this variational distance, and I'll consider top one accuracy, just because this number is a little bit hard to interpret. If I tell you this is 0.4, it's hard to understand, whereas 1 or 0 is easy to understand. Do they make the same top one prediction or they don't, right? So just maybe one final piece of terminology, which I've already mentioned before. I'm going to call the optimal rule, or rather, I'm now going to quantify what I meant by the optimal rule now in light of what we just talked about. This here, P of T conditioned on the context, this is the next token distribution of my model, my transformer, right? So for any context, the tired dog, this is the output probability distribution on the possible next set of tokens. The tired dog ran, slept, barked, whatever, right? Those have, reasonable probability mass on them. I go through my rule set, whatever they are, the subgram rules, the suffix rules, the ones that have marginalization. I go through all of them. I pick the one that minimizes the distance, right? Each of these ones are also probability distributions on tokens, again, based on purely training data statistics, based on the relative counts of T. And the one that minimizes this distance is the one I call the optimal rule, using, say, the variational distance. Okay, so that's in some sense the one that best describes the LLM. For each context, I have now a candidate optimal rule, and then the question is, does it make the same prediction as the transformer? Okay, so this has maybe been a little bit abstract, so I want to go now into granular detail on how this procedure works. So let's go through a specific example here. So here's a holdout story from TinyStories on from the validation data set. So here's the story token by token. Here's the ground truth, and you can see it's like a children's story. There's the beginning of sentence token. Once upon a time in a big forest there lived a rhinoceros named Roxy. Roxy lived to climb the blah blah. Okay, and I'm going to walk through sort of what this table is summarizing here. This is a table from my paper. There's a lot of information on it. Let me go through it one by one. What we're going to see here is how the transformer, well, what n-gram rule best describes the transformer at every step. So let's start from the beginning. So one by one, when the transformer is evaluating this story, right? It first receives the beginning of sentence token and then makes a prediction. And then it receives beginning of sentence once, makes a prediction upon, and then a next prediction, right? One step by step. And as we go along, let's look at the first four. It's saying that the n-gram rule, which best matches what the transformer is doing, are each of these contexts, which is not surprising because it's using the entire context. So for example, when I feed the transformer once upon, beginning of sentence once upon A, it has some output probability distribution of the next token. Once upon a time, time might be very high, right? These are all probability vectors, and what I'm saying is that each of these vectors are closest to the n-gram rule given by this context. I could have chosen a different context where I say drop some of these tokens, but those will give me worse predictors. The best n-gram rule was the one that used all four tokens. Okay. This is in contrast to this example here, which I'm about to get to, which is interesting now. So now when I feed the transformer 5, right? Beginning of sentence once upon a time. Okay, this is now some probability distribution on the next token, right? And I have all these ways of forming n-gram rules from this previous context. I could have taken all 5 tokens, but in this case, actually the better rule, it turns out, that's what this column is saying, the better rule was this upon star time. Okay, and what this is saying is the following. Upon star time, if I go through the data set, I see that in the training data, upon a time occurs many, many times. And some of these stories are a little bit ungrammatical. So in the training data, you had things like upon the time, upon in time, upon a time. I don't know why these two actually, these A's had different tokenizations, but okay, I mean, that's some weird thing. But okay, they end up counting as different things. And you have these other contexts that sort of match this wildcard character. And what this is saying is that this probability distribution is basically a weighted average of all these probability distributions, right? Because each of these contexts have a next token distribution. This context has a next token distribution as all these other ones. And it turns out that the probability distribution given by this guy is best matched by the corresponding weighted combination of these ones versus, some other kind of n-gram context you could have formed. Let me pause here and see are there any questions about this?
So there are some questions in the chat.
Oh, I didn't see. Okay.
So on the bottom right, there is meeting tools, and then there is Q&A.
Let's see. For some reason, I can't seem to click. Oh, sorry. No, never mind. Wait. Q&A. Okay. Okay, let me take it. Let's see. Do these rules hold across different scales? So there's a fixed set of rules. They're not model dependent, right? Because a rule is of the form how am I going to treat each tokens? So they don't depend on the model. So I'm not sure what that question is asking. I assume that the 79% matching statistic is without the decoding methods used. Is that right? I'm not actually sure what that question means. It's, for example, in this example, for what we see here, I didn't indicate this, but if there's a misprediction between the optimal rule and the predictive distribution, I will highlight one of these tokens in red. So what this is, since you don't see any tokens in red here, what this is saying is that as I go through these tokens, actually all these rules make the same top one prediction as the transformer. So in this case, it turns out that this rule makes the same top one prediction as the transformer, which also ends up being the ground truth. Sorry, there's a lot of information here that's in my paper, but I just took a screenshot here. So it turns out that in this case, both the ground truth, sorry, okay, actually, can you see? Okay, right. Both the transformer and the optimal rule and the ground truth make the prediction of a comma. Okay. Let me go to an example where this is. Let me go to the next slide, for example. That gives an example of where this is different. So so in this case, I go further down, and I have this context. I have this rule here, which is lived a star in star arrays. Okay. I go through the training data and I grab all the contexts which match that. It turns out it's always, you know, RH and OC, right? Rhinoceros. But you see now in this example, I actually show you what the next token distribution is. So see arrays period, arrays named, arrays in, arrays who, arrays called. In this case, the top one prediction of the rule is to predict period because it occurs 23 times. But it turns out that the model predicts named. And so this is an example where the transformer and the optimal rule disagree. So let me repeat that because there's a lot going on here, right? So I have this story, right? The transformer is fed this story, goes blah 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 blah. Okay, named. Okay, so I have once upon a time in a big forest there lived a rhinoceros. Okay, the transformer predicts named. Okay, and then you ask yourself, okay, I have all these possible n-gram statistics from the context, right? And I look at the n-gram rule that best matches the transformer prediction. And it turns out to be this rule. That's what this column is. But this rule predicts period because this rule you see here means I'm going to grab all the contexts that match this pattern, which is lived a rhinoceros. And when I grab that context, the resulting probability distribution has the most mass on period because period has the highest count in this context. So here's an example where the top one prediction of the best rule doesn't match the transformer. And that's why I called it red here. But everywhere else that's not red, so outside these three tokens, the best rule, which is given in this column, has the top one prediction matching the transformer. So anyways, if you're interested in the example, basically you can look at my paper when you have time and kind of go through this and you can see, oh, you know, here are all these n-grams that when you look at their top one prediction, match the transformer. And you can see here's a manifestation of that 79% statistic that I quoted earlier, because on average, 79% of the time, whatever rule you see here makes the same prediction as the transformer. So this is basically a concrete way of seeing how n-grammy the transformer is. So that was the point of this example. You can kind of again go through this and just kind of look at what is it that's in the context that has training data statistics that are sort of matching the transformer prediction, again at the top one level. So so that's sort of a way of seeing how stochastic parity the transformer is, because everything on the right hand side is basically encoding training data statistics. Let me see if there's any other questions that might make sense to take for now. Okay, yeah, those. Are those rules like a weak version of regex? Yeah, I mean, as you can see, it is basically like a regex. You can think of it as like the following. What I'm doing in my paper is I'm saying, I'm feeding the transformer text. I'm doing a localized regex expression matching up to 7 tokens because famously n-grams don't scale well. So when you have 7 tokens, you're already getting into very computationally expensive burdens where you have to kind of look through the training data and do all this kind of matching. It's very expensive. And you're saying, oh, I'm finding sort of the best regex match as measured by this variational distance on resulting probability distributions. You find that regex match is what you see here. And then you ask, once I get that match, do the resulting distributions make the same top one prediction? And the answer is yes, 79% of the time. Okay, so that I'm just kind of skimming through the questions here because there's quite a bit. Maybe I'll go back through them later once I maybe at the end. Let's see. Okay, let me just move on because I guess there's quite a few questions there. It might bog us down, but maybe I'll revisit at the end. But I hope this makes sense. Yeah, I'm basically quantifying and showing a visual demonstration of how n-grammy the transformer is essentially. Okay. So, yeah, there's just more examples of this. Let's see. Okay. Yeah. So here's just another table that summarizes this. I have different families of rules. What I saw, what I presented in the previous slide was the case when I had the strongest set of rules. Basically, I considered all possible operations, keep, drop, or marginalize, and I consider up to 7 tokens. And then you get this 78% statistic where the rules match, the optimal rule matches the transformer top one prediction. And this table just shows how that number changes as you soften the rule set, right? So if you had fewer sets of rules, you know, less context, how these numbers change. So you can have fewer tokens of context, or you can have weaker sets of rules. But if I choose 7, then I got this 78% number. This is using the variational distance to measure the optimal rule. If you use L infinity distance, a different metric to grab the rule, so L infinity just means the distance between 2 vectors is given by the maximum of the absolute value of the differences. This number is 79%. I just use a different distance just to kind of show that there isn't something anomalous with the distance metric. It's pretty robust. So in the appendix, I have this number as 79 because I use a slightly different distance. But okay, I just wanted to have this table to show how these numbers change when you vary your rule sets. One thing to note is that this model, which is a 150 million parameter model, its ground truth accuracy is 69.6%. And I just have that number just because it's hard to know what the 78 means. Is it a high number? Is it a small number? Right? Like I don't know what this number really means in some sense relative to other numbers that one might be used to. But there's a sense in which it's quite high because it's higher than the ground truth accuracy, right? So there's a sense in which you can regard this as a high number. If this were lower than 69.6%, maybe it wouldn't be that impressive. But because it's quite higher than 69.6%, there's a sense in which, these n-grams are sort of capturing the top one prediction more often than even the ground truth. In the sense that this thing is capturing or describing the transformer behavior. Okay. This is just another table just quantifying the way in which these rules are approximating the transformer distance. Here I just plot the distance itself rather than the top one accuracy, and you can see that these numbers are decreasing. And the reason I do this is because you can actually do what I just did in a very, very stupid and cheating way. For example, my vocabulary set was around 32,000, and you could have a very, very dumb set of rules, which is the following. I have 32,000 rules, a rule for each token in my vocabulary, right? And if you did that, then of course at every step there is going to be some rule whose top one prediction matches your transformer prediction, because you have a rule for every token in your vocabulary. Of course, there's going to be a rule whose top one is whatever the transformer is doing, because you just have every possible token, right? Two things. One, I don't have 32,000 rules. I have more like on the order of 1,000 or something. So I have a much fewer set of rules. But second, if you did this one hot rule for every token, the one hot distribution will in general be quite far from the prediction that your transformer makes, just because your transformer usually has weight on quite a few tokens, because in general there are many possible completions. And so the one hot distribution will in general be quite far from distributions that have lots of mass on other tokens. And this is just to show that you are capturing kind of the probability mass of the non-leading tokens, because these numbers are decreasing, right? So this is just a kind of a way of showing that this isn't like completely cheating in some sense. But yeah, all I'm trying to say is there's a way you could easily cheat, and this method, these numbers decreasing suggest that it's not kind of just picking the top token without capturing any sort of subleading statistics. Okay. There's a version of this on Wikipedia, so you can play the same game with Wikipedia, using rules with respect to again the same set of rules, but now you just have Wikipedia data, right? You just go eval time, you crawl through the Wikipedia training data and aggregate statistics and find the best rule. You can play the same game, and the top one accuracy you get when you use rules formulated from 7 tokens using all the possible operations, you get 67.7%. I think here the top one accuracy of the model I trained was maybe 64%. So 67 again is higher than 64. So yeah. Anyways, this is just kind of a way of quantifying again how n-grams are describing or modeling or capturing transformer predictions. Maybe in the interest of time, let's see. Let's see. Maybe I'll just skip this one. Actually, well, okay. I think we do have enough time. Okay, so result number 2. Now let me just go deeper into these other results. This thing I said about low variance and being approximated by a rule. Here's just a histogram where I look at all 7-gram contacts in TinyStories. On the x-axis, I plot the count on a log scale of how often that context occurs in the training data. And on the y-axis, I look at the variance across 5 runs of the model predictions. So what I do here is I basically take the pairwise averaged, or yeah, I think I take the pairwise average distance between the model predictions, or maybe just the variance in terms of the distances themselves between the individual model predictions given that context. And what you can see is the following. For contexts that occur, say, 1 million times, the variance is quite small, as you might expect. But what's actually interesting is that even for contexts that occur a single time, what's interesting is how much spread there is, right? So there could be a 7-token context that occurs once. And for this one, which has 0 variance, it's basically saying all 5 models actually make the same prediction on this unique context. Whereas for this token up here, it also occurs only once, but these models differ wildly these 5 models differ wildly in their predictions. So it's kind of interesting to see that as you start moving away from frequently occurring context, there's a large spread in terms of how much the models vary in their predictions based on that context. So sort of count isn't a very good indicator of whether the predictions will be quite consistent, as you kind of can see from this low R-squared score. But one thing I observed is if you put on the x-axis the model variance and the y-axis the distance to the optimal rule, in this case I just use these suffix rules, things that have lower model variance have lower optimal rule distance. How do I interpret this plot? It's basically saying each of these points is a context, and the more those models agree, those 5 models on different runs agree with on the context, then there's likely to be a rule such that the distance of that rule is quite small. In other words, as you start going to 0, the bias from it being away from an n-gram rule, there basically is no bias, right? If there was a bias, this thing would be kind of offset. It's basically saying no matter, all these models agree, but they're still far away from an n-gram rule. The fact that as the models agree more, they get closer and closer to some n-gram rule. That's what you see on this plot, okay? And if you had just used the simplest n-gram rule, which is to use all the tokens in the context, you see a much larger spread. So another thing that's captured by this plot is basically saying, oh, you give me 7 tokens of context. It's not always using all 7. It can use some subset, and this is just the subset given by suffixes. And already there, adding those rules reduces the variance or the distance by many of these tokens. So this is just a way of kind of capturing, at a quantitative level, how n-gram rules are approximating transformer predictions. This is just kind of a plot that sort of captures that. Okay, anyways, it's a bit technical. You can read the paper if you want to look into this more, but this is just a way of giving more quantitative analysis of being approximated by n-gram rules. Result 3 is this curriculum learning result that I mentioned earlier. So here I have rule context length, right? So again, I have families of rules that are more and more complex, right? I have rules where I just look at 1 token of context, so a bigram rule, 2 tokens of context, a trigram rule, all the way up to 7, right? And you can see here, let's focus on this left plot here. As I train, let's look at the blue, green, and blue, orange, and green, and red, corresponding to bigram, trigram, 4 and 5 gram rules. They start improving over time, which means that the transformer is getting better and better approximated by these rules because this distance is going down, but they start going up as you train longer. So what this is saying is that eventually the model is being less, the optimal 2, 3, 4, 5 gram rule is getting further and further away from the transformer. And you could think of that as because it's using more context, right? So these rules that use more context continue to improve or not get worse. Okay, so that was this is sort of a quantification of that cartoon I had earlier, where when you train, you start off learning simple rules, and then as you train longer, you start discarding them for more complex rules. And that's exactly kind of captured by this leftmost plot here, where you have this U-shaped curve measuring the distance between simple rules and the transformer predictions, but then these curves that keep going downward for the more complex one. And the other plots are just more manifestations of that. Let me get to this overfitting one, because I think it's quite interesting. This is the last result. So given a context, you can form, I'll just let piece of n denote the simple, the simple n-gram rule where I used as context the n most recent tokens. So this is your vanilla n+1 gram rule. And if I do that, let's see. Okay, so what is this plot saying, and how is it detecting overfitting? So the gray is the full transformer model, and by full I just mean it's just the vanilla transformer. Okay, I train a transformer for many steps. The train loss keeps going down, but eventually it overfits, and that's what this dotted line going up is. It's the validation loss. What are these other curves that I didn't describe earlier? What are these measuring? This is measuring is I'm going to take the transformer and only evaluate it on the n most recent tokens. That's why this is called model context length. So in other words, I'm just going to go through the training data and only feed to the transformer the most recent token, right? So every time it makes a next token prediction, it only sees the most current token. And likewise for 2, it only sees the 2 most recent tokens, green, 3, et cetera, right? So you're kind of masking out or ignoring all the tokens beyond that, okay? And what you see here is that if you only give the transformer a limited number of tokens, its performance deteriorates as you train longer when it has this limited context. And let's think about what's actually going on here. Like, there's a very simple way to understand this. Let's think about this. What is overfitting, right? Typically, these transformers have a sequence length of around 2048. I think that was the sequence length that I used for training these models. When you're overfitting, what's going on? It's basically saying that to predict the next token, I'm actually using all of the context to predict the next token. It would be like learning English by predicting the next token based on the exact text that you've read or learned up to that token, right? In reality, when you speak English or write English, you're using some mix of long and short context, right? So, the tired dog, you have a pretty good idea of what the next token will be. You don't need to know the pages and pages of text that preceded the tired dog, right? When a model is overfitting, what's happening is that it's actually forcing itself to use all that previous context. Because if you think about it, the way you want to minimize the train loss, if you truly want to make the train loss the lowest possible, what you would do is you'd be an infinitely long n-gram model, because an infinitely long n-gram model is the one whose next token prediction exactly mirrors the training data, right? The cross-entry loss between 2 distributions P and Q is minimized when Q is equal to P, which basically means the next token prediction has the same statistic as the training data, which means that any context which occurs uniquely in the training data, if it predicts the next token with probability 1, you should also do that as a model, which is quite absurd if you think about it. A good language model would never do that, because a good language model should make a prediction of the next token also based on local context. Just like I said, the tired dog, there should be weight on slept, ran, bark, etc. But if your model wants to achieve the lowest train loss, if the tired dog was preceded by a paragraph of text, and in the training data there was a unique token that occurred after that entire context, to minimize the train loss, you would just be the one hot prediction on whatever that token is, right? So as you're going into that overfitting regime where you're just regurgitating the training data, that's what's happening here, this overfitting. The model is now deteriorating on its n-gram statistics for low n, because as I said, it's basically memorizing the training data, and that's compromising its ability to capture local statistics. And that's why when you feed it short context, it's doing worse. Okay, so I hope that simple explanation explains what's going on here. But the significance of this result, again, is that you see, using short n-grams, what you've basically done is found a way to detect overfitting without using any holdout data. Because overfitting is basically saying, I'm memorizing long context, and the way you could detect memorization is just to say, feed it short context, again, from the training data, and you will see deteriorating performance on the train set, right? Again, on the short context, but not the full context. Okay, so that's the significance of this result. I think it's pretty cool, and it also has a pretty nice interpretation. Yeah, so overfitting equals memorizing long context at the expense of learning subcontext statistics. Okay, that was my last slide. Yeah, I'm happy to take any live questions. I can also scroll out. There's a lot of questions in the side chat. I don't know how to prioritize. I don't know. Hopefully some of the questions that were asked during the talk have been answered as the talk went on, but maybe I'll take a live hand. Yeah, Wesley?
Sure. Did you notice any types of predictions where the n-gram is like consistently doing worse than the transformer?
Well, sorry, what do you mean by that?
Like different like math or technology or coding? Is there like specific?
Oh, I see.
Words?
I mean, yeah. I mean, I only did TinyStories and Wikipedia, so I don't have other data sets to compare it to. So yeah. Yeah. I'm just going to skim through some on the right-hand side and see if there's any that stand out to me. Okay, there was a question by Rasif about interpretability. Yes, so this is why at the beginning I had this sort of philosophical primer on description versus explanation. I want to emphasize, and actually it's important, I'll go back a few slides. These are descriptions, not explanations, right? So you can see, for example, like even something as simple as this. So here's this rule here. There can be many rules, right? Because the optimal rule isn't unique, okay? And here you can see, for example, lived a star in star arrays. It turns out this regex pattern always grabs, you know, lived a rhinoceros. So there's another rule. This one was the rule where I have plus plus star plus star plus. Plus means I just keep the token. But this rule coincides with all pluses because it turns out that there was a unique match to this. So you can't read, all I'm trying to say is you can't read too much into, you know, this list on the right, because there could be many other rules that give you the same rule or also the same prediction, but which look nothing like this in principle. And this is just to say, look, like there are many parts of the context which can give you the same next token, right? Like this is very intuitive. Like suppose you have a very long paragraph and you want to predict the next token. Like that token could be attributed to the most recent part of the text, or maybe some very far part of the text. And this methodology doesn't distinguish that, because this methodology is just cares about the statistics of the next token, whether that comes from recent text or far away text. So that's why I was careful to make it in terms of description, not explanation. An explanation would sort of be some kind of circuitry that says, oh, the network, you know, processed these tokens and focused its attention on this part of the text, and that's why this part explains it or causes it. I'm just saying, I'm just giving you a description, right? Another way to think about this is like, you know, in the real world, there could be many descriptions for the same phenomenon, right? Like why did it rain? Because there's precipitation. Another description is because Zeus was angry, right? Those are two descriptions, very different descriptions, but they're both explaining the same phenomenon, right? And likewise here, you can have very different n-grams giving the same description, even though they're very different n-grams. So maybe that's just a caution on interpretability. Yeah. Okay. Let's see. Okay, it's something about replicate my results. This stuff is open source, so there's a GitHub repo also linked on my paper where I basically process the TinyStories data set in such a way that you can rerun these results. The most expensive part of this is just aggregating all these n-gram statistics, and that requires a huge map reduce because you have to gather all these statistics. So basically, I do that. Yeah, in some way or shape, I upload that data, make that data available, so you could basically rerun this. You could regenerate this stuff on your own. What you see here. So yeah, if you want to play with this, feel free. Yes, Lima.
How are you defining the optimal rule for each of the tokens?
Yeah, so that was something I described. You know, it's this one. It's the one that has the minimal distance to the transformer prediction, right? So let's go back to the very tired, or the tired dog, right? There's going to be some mass on slept, some on barked, some mass on ran. Let's be simple. Suppose it was exactly all three with 1/3 weight, right? And then you go through all your n-grams in your rules and you see what vector it has on the space of tokens, right? There might be a vector that has no mass on slept, barked, and ran. And there could be one that assigns a half to the first token and a half to the second token and 0 to the third. And that's going to be closer, you know, to the uniform distribution on those three tokens than one that assigns no weight to those tokens, right? And so that would give you a better rule. And then you just go through all your rules and find the one that gives you the best approximation of that one. That is the optimal rule.
So are you like defining the rules? Like I remember you said that you have around 1,000 of them.
Yeah, yeah, if you go through, if you have 7, this one is going to be around 1,000. And then if you decrease M or look at these ones, they're fewer. A rule is a template. Think about it that way. A rule is basically this sigma, and each context gives you a different instantiation of that rule, because each context gives you a different matching expression in the training data, which gives you a different probability vector. Yeah.
Thank you.
I guess, are we at time?
Yes. So I think we can conclude the session here before